want to take a few minutes to talk about something new that I made today. I made a 16-channel analog multiplexer board. And the idea here is so that you can do a hand wire build of my analog keyboard and use the analog keyboard firmware with it and my 3D printed switches. So if you wanted to make like a Dactyl Manuform or just design your own and print it out without having to make your own PCB, you can do that. So let's go over this for a moment. And before I do, let's talk about what exists in the market today. This is a 74HC4067 chip. Now you can get them from various manufacturers. It's been around for a very long time now. And this is what your standard breakout looks like for it. And for reference, I should probably talk about how this works. You've got 4 signal lines, you got S0 through S3, and depending on which ones are high or low, is going to control which pin is active at the moment. And this thing just works as, it's just a bunch of flip-flops internally. There's nothing really special about it. So when you say enable channel 0 here, this signal goes through the chip all the way back to your microcontroller through the signal in out pin, which is this SIG line here. So that's how it works. And it goes really, really fast. So for reference, my Risky Board firmware running on the Black Pill can check all of these pins in like, I want to say 200 milliseconds, 200 microseconds. Yeah, it's super duper fast. So you can read every single channel, the state of every single channel, in under a millisecond, easy on most microcontrollers. And which is what makes it great, because you can turn one analog input pin on your microcontroller into 16. So for every pin you get 16 inputs, which is sweet. That's how my Risky Board firmware works. It just enumerates all of them. And what's nice too is if you tie S0, right? How do I explain this? So you can have many of these chips lined up together and have them all on the same 4 lines. So on your microcontroller, you still need 4 GPIO, right, to control this thing. But no matter how many of these you have, you still only need 4 GPIO. Because what you do is you enable channel 0, and then you read channel 0 on analog multiplexer 0, and then you read channel 0 on analog multiplexer 1, and then 2, and then 3. And then when you're done reading all of your analog multiplexers, you switch it over to channel 1, and then you repeat for every single channel. And mine does that for 96 channels in like 200 milliseconds. It's 200 microseconds. Like I was telling you, it's like it'll read that many channels, so you can get your 1 sub-millisecond response time on your keyboard and also be able to analog and all the sweetness where you can set your own actuation point. But this is the key to making that work, is this thing. So if you want to do a hand-wired keyboard, you're going to need something like this. But this thing sucks. Oh my God, I got a bunch of them, and they're terrible. First of all, let's talk about this thing for a second. So one of the things about analog signals is that they're very sensitive. So if you've got like some EMI, electromagnetic interference going on nearby, these pins are going to pick it up. And the longer these traces, the more likely they are going to be, they're like antennas, right? Another problem is when you flip these flip-flops internally that quickly, it tends to collect it still has a little bit remaining voltage left over in the signal outline from the previous flip-flop if you have a floating pin. So let's say we had all of our pins hooked up except for channel 11 here. Channel 11 was just floating. We had it plugged into nothing. And we switch from channel 10 to channel 11, and we skip over channel 11 and we do channel 12. In the microseconds that happens, there's some voltage here that will stick around and make it all the way over to channel 12 from channel 10, because basically leaving these untied messes up the internal signaling of this thing if you switch really quickly. If you go slow, it's not going to matter. But if you're doing like a keyboard where you're scanning a bazillion analog inputs at once, under a millisecond, it's going to mess with your signal. So the way to work around that is you need to tie every one of these unused pins to ground. But that's a problem on a board like this, because you've only got 1 ground pin here. So let's say that we weren't using 11, 10, and 9 here. We could just run a wire to ground, but oops, we just created an antenna. And it's a big pain in the butt to have to run all these big wires to ground. It would be so much simpler if there was some sort of way to tie this to ground right here. Wouldn't that be nice? Well, I did that. That's what this is. Let me flip it around and you'll see what you can do. Ta-da! Tie unused pins to ground, right? So if we don't use any given pin, like say we're not using pin 1 or pin 9, right? We can just put a little bit of solder right there to bridge that little pad there, and bam, we just tied signal pin 9 to ground. Same for any one of these. So you just flip the little board over, and whatever pin you're not using, just put a little bit of solder to bridge these two pads together, and bam, you just solve that problem. You're not going to be collecting random voltage signals from nothing from unused pins. Another thing that I designed about this, it may look a little strange, especially compared to that other board. Let me bring that up again. No, wrong one. Here we go. So you can see I've got all these pins on the right-hand side here. On mine, I've got those duplicated, right? I've got on the left here, we've got ground and the voltage, and this will work with 3.3 volts or 5 volts. I think the chip goes all the way up to 11 volts or something like that. It'll work with any of them. But then we've got the signal lines, an enable pin, which nobody uses, let's be honest. We're just going to keep it enabled all the time. It's not like it saves power. If it did save power, then we might use it, but it doesn't actually. So why would you turn it off? It doesn't make sense. Anyways, and then we've got the signal line. And you notice that the signal line and the enable pin are not duplicated on the right here, and that's because there's no point, right? We want this, they're unique to this chip. So the idea here is you can daisy chain this board one to the next, and I actually went ahead and did that. So let's have a look. And I called it the Multitudio, but that's just an early name. Who knows what I'll call it in the end. Multitudio is really the name for. I wanted to make up like a microcontroller board that had 8 of these built in and have 128 analog inputs, but I don't know if that's going to be realistic with the current chip market. So as you can see, I've chained 6 of these together for a total of 96 analog inputs, right? Which would cover, most keyboards that you would want to hand wire these days. Most folks tend to do like splits and things like that. And I've chained them together so the signals go across. But if you were to do this, you'd probably want to feed the voltage and the ground in the center here, so as to minimize voltage loss going across. But I did put a capacitor on every single one, just in case you did want to rely on the voltage coming across to stay nice and even. And this is not, you'll notice this is not mouse bites. Mouse bites with analog signaling and things like that can actually cause some trouble. So I made it so that you're meant to saw this off. So it works like a one of those STM32 Nucleo boards where you can saw it off, get like a hacksaw, or if you're really careful with some strong cutters, you could do it. But you don't want to just bend it and break it off. In fact, it might make these thicker. We'll see. I'm gonna order it. We'll see how it goes. So this baby should let you make monstrously large keyboards, and even like musical keyboards or anything that you want to use as with analog. You need a lot of analog inputs. All right, so that's how that thing works, and you've got the grounding pins on the back. The other nice thing about these chips that you may not know, these 4067 analog multiplexer chips, is that they work with capacitive touch too. Now, the only trick there is you can't change the channel as fast as you can with Hall effect sensors. You got to put a little delay in there while you read the signals, because the way that capacitive touch pins work, like let's say you've got an ESP32 and it's got a bunch of those pins built in where you can do capacitive touch sensing. The way it works is based on timing, and that timing is in the microseconds range, but your micro might be faster than that, right? So you just want to make sure that you can read that pins. You just want to put just a few microseconds delay when you switch channels, so that you can collect all the capacitive touch sensing. But you really can have 96 with this setup, 96 capacitive touch sensing pins with this thing. And I've made it nice and compact, and I do believe it's like 33 by 26. Let's have a look. Oh, and here's this complicated thing is just this tiny little schema, by the way. That's all there is to it. Got 3 mounting holes. Let's go back to the PCB view. All right, let's measure this thing. Because I forget how big it is. I'll go down here. 0 degrees. Yeah, it's 26. It's like 26 and a half by, and that half is just the way it worked out. I didn't really do that on purpose. And 32 and a half. So it's pretty small. It's much more compact than than this thing, which is way too long. It's annoyingly long and wide. I've worked with it a bunch of times. I don't like how long it is. It's way too long. This is much better, because you're just gonna solder your wire right in there probably. You're not going to put like a header on there or anything. You just solder the wire right in there. And there's no reason why you need to have every wire separated out in such a wide array. It's silly. You can do it right here. So that should work out really good. And that's what I've been working on. So if you guys have any questions about it, I do plan to order some of these soon, and then I'm going to make a hand wired. I don't know, maybe like just as a test, like an ortholinear, maybe something quick and easy. Ortholinear is nice and easy to make, but maybe I'll do a split keyboard or something, and I'll do it all with just a straight up black pill that you could buy, and some of these, and some Holophix sensors that I have lying around, like ones that'll hand solder. So it'll be a truly hand solder board, except for the fact that the chip I'm going to get assembled. I'm going to have it put on here. Not that this is too bad. This is a TSSOP 26, I think, which is, you can solder that by hand. But of course, as usual, I'll choose like the dust-sized capacitor, just because I know it's going to get assembled, and I don't care. I'd rather have a small one than a big one, right? Why not? Make it nice and tiny. And the enable pin is bound to ground through a resistor, so it should still, it's going to be always enabled unless you give it a high signal. Then that's it. That's how that works. Any questions, feel free to ask. I will be happy to answer them. And feel free to ask me on Discord too, if you want a quicker response. All right, that's it.